Good morning, sir. Today I am presenting experiment 4, uniform quantization and PCM. The main objective of the experiment are to implement uniform quantization and PCM encoding and to study the relationship between quantization error and SQNR. First, I have generated a sinusoidal signal using Python. The sampling frequency is 10 kHz and signal frequency is 100 Hz. After generating the sinusoid, I have normalized the signal so that its amplitude lies between -1 and 1. After generating the sinusoid, I have normalized so -1 and 1 as required in the experiment. Next, I have implemented a uniform quantizer. I have tested quantizer for 2, 3, 4, 6 and 8 bits. For an n-bit quantizer, the number of quantization level is given by L equals to 2 to the power n. For example, for 2 bits there are 4 levels and for 8 bits there are 256 levels. For every input sample, the program calculates a quantizer index. The index is always kept between 0 and L minus 1. This also satisfies the mandatory validation given in the experiment. After obtaining the quantizer index, I converted each index into its corresponding binary PCM word. The PCM word contains exactly n bits. For example, there when n equals to 3, the PCM word contains 3 binary digits. I have also included a validation to make sure that the PCM word length is equal to the number of bits. Now, the graph. First, we have to run. So this is the original quantized waveform. The continuous looking curve represents the original sinusoid signal, where the staircase signal represents the quantized signal. The difference between the two signals is the quantization error. So this graph shows the staircase characteristics of the uniform quantizer. The main input amplitude is mapped to discrete output amplitude levels. As the number of bits increases, the number of levels increases and quantization becomes more accurate. So this is a quantization error histogram. The quantization error is calculated by subtracting the quantized signal from the original signal. The error becomes smaller when we use more quantization levels. So next, I have calculated the mean square error or MSE using the average square quantization error. I have also calculated the SQNR, which is signal to quantization noise ratio. The formula is SQNR equals to 10 log 10 of signal power divided by noise power. The graph shows SQNR versus the number of bits. The theoretical value for the full-scale sinusoidal signal is approximately SQNR equals to 6.02 n plus 1.76 decibel. We can observe the SQNR increases as the number of bits increases. Therefore, increasing the number of bits reduces quantization noise and improves the quality of the reconstructed signal. To conclude, I successfully implemented uniform quantization and PCM encoding for 2, 3, 6 and 8 bits. I verified the quantizer indices and the PCM word lengths using the mandatory validation. I also calculated MSE and SQNR and compared the measured SQNR with theoretical value. This experiment shows the higher bit resolution gives more quantization levels, lower quantization and high SQNR. Thank you, sir.